All right, let's dive right in. Today, we're exploring the wild early days of Bitcoin and uncovering a couple of hidden traps, sneaky problems that could take a perfectly valid transaction and just break it. And we're not talking about some obscure bugs here. These were fundamental issues that really forced Bitcoin to evolve. So let's get into it.
It really all boils down to this one question. I mean, you digitally sign something, you expect that to be a rock-solid guarantee, right? An unbreakable mathematical promise. But what if that very signature, that proof, could actually be part of the trap? Or what if the promise itself could be, well, shapeshifted by a total stranger after the fact? That's the mystery we're going to solve. So to get our heads around this, let's bring in our favorite characters, Alice and Bob. They want to set up a financial deal on Bitcoin. And, the whole point of using a blockchain is to get rid of the middleman, to not have to trust anyone. So their goal is to craft a deal that's guaranteed to work, no matter who does what. This right here is the holy grail, a trustless contract. It's an agreement that doesn't depend on you hoping the other person is a good guy. Nope, it's all about the code. The idea is simple. If Alice puts her money in and Bob decides to bail, poof, Alice gets her money back automatically. The system itself is the referee.
Okay, so Alice and Bob, they cook up this plan. And on the surface, it seems absolutely brilliant. It's a two-step process, a clever little dance of transactions designed to be perfectly safe. But hidden inside that cleverness is a critical, deal-breaking flaw. So here's the plan. First, they create and completely sign the refund transaction. Think of this as their emergency escape hatch. Once that refund is signed, sealed, and delivered, only then do they go ahead and sign the main funding transaction, the one that actually moves the money. Sounds foolproof, doesn't it? Everybody has their get-out-of-jail-free card before a single penny is actually at risk.
I mean, that logic seems perfect. It protects everyone involved. But like with so many things, especially in crypto, the devil is in the details. There's a nasty little paradox hiding just beneath the surface. And here it is. Here's the catch. For that refund transaction, let's call it TX1, to work, it has to spend the money from the funding transaction, TX0. And to do that, it needs to know the unique address of TX0. It needs its transaction ID, the TX ID. It has to point directly at the money it's supposed to give back. Now this is the killer detail. A transaction's ID isn't just some random number. It's a cryptographic fingerprint, a hash of everything inside that transaction. The amounts, the addresses, and, crucially, the signatures that authorize it. The ID literally does not exist until after everyone has signed. And bam, there it is, the paradox. You can't create the refund because you don't have the ID of the funding transaction yet. But your whole safety plan depends on creating the refund before you sign the funding transaction. It's a classic chicken and egg problem. You're completely stuck. This whole mess has a name. It's a circular dependency. The logic just eats itself, making the plan impossible. And the big takeaway here is that their trustless contract is broken. Someone has to go first. Someone has to sign and just trust the other person will follow through, which completely defeats the whole purpose of using Bitcoin for this in the first place.
Okay, so let's just pretend for a second you figure out a way around that dependency trap. You're not out of the woods yet, because a second, even weirder problem is waiting for you. This one doesn't stop you from making the deal. It lets a total stranger break it after you've already shaken hands. This bizarre idea is called malleability. The best way to think about it is with language, right? You can say, give Bob $2, or you could say, send a sum of $2 to Bob. The meaning is exactly the same, but the words you used, the actual data, are different. Well, it turns out Bitcoin scripting language works the same way.
And just take a look at this. It's a perfect example. All these different opcodes and hex representations, they all mean the exact same thing to the Bitcoin network. They all just mean the number 2. Each one is totally valid, but you can see they're written differently in the raw data. It seems like a tiny nerdy detail, but trust me, the consequences are enormous. So why on earth does this matter? Because remember how the transaction ID is a fingerprint of all the data? Well, if you change even one single byte, like switching from one way of writing 2 to another, you get a completely different fingerprint, a totally different TX ID. Even though the transaction does the exact same thing, pays the same amount to the same person. And here's where it becomes a disaster. Let's walk through it. Alice pays Bob in transaction A. Bob sees the money coming, so he immediately creates transaction B to pay Carol, spending the funds from transaction A. But then, some random person on the network sees Alice's transaction. They just tweak how a number is written and rebroadcast this slightly mutated version. If the miners pick up the stranger's version first, Alice's original transaction is just gone. It never happened. Which means Bob's payment to Carol is now pointing to a ghost transaction. It's invalid, his promise is broken, and Carol gets nothing. This crazy phenomenon has a name: unwanted third-party malleability. Let's break that down. Third party because it's done by a stranger, someone not involved. And unwanted because, well, it's destructive. It shatters the chain of promises you're trying to build.
So, I know this is deep in the technical weeds, but why should we care about these glitches from way back when? Because these aren't just academic puzzles. They're fundamental cracks in the foundation. You can't build a skyscraper on shaky ground, and you can't build a global financial system on transactions that can just change. So let's just put these two traps side by side. The circular dependency is a problem of creation. It literally stops you from being able to build certain kinds of trustless contracts. Malleability, on the other hand, is a problem of destruction. It lets a stranger come in and smash a perfectly good contract after it's already built. Two different problems, two different causes, but they both lead to a brittle, unreliable system. At the end of the day, if Bitcoin is ever going to be more than just simple payments, if you want to build amazing things like the Lightning Network or other complex smart contracts, the most basic building blocks have to be absolutely rock solid. The transaction IDs have to be stable, predictable, and final. Without that guarantee, the whole house of cards is just too fragile. And that really leaves us with this final, massive question. If the very identity of a transaction isn't set in stone, if it can be mutated out from under you, can you really build anything meaningful on top of it? The search for an answer to this very question led to one of the biggest and most controversial upgrades in Bitcoin's history. But that is a story for another time.